What might be the first human sound aliens ever hear? It might be the sound of laughter, because laughter is on this record. It's called The Sounds of Earth, and the real version is attached to the NASA Voyager spacecraft, the most distant man-made object from Earth. Why would we be trying to greet aliens with laughter? Well, because laughter is one of mankind's most important sound communications. Humans and animals are constantly sending messages to each other in different ways. In these lectures, I'm going to be showing you where this incredible urge to communicate comes from and why it's essential for the survival of so many species on Earth. Welcome to the language of life. Welcome to the 2017 Royal Institution Christmas Lectures. I'm Professor Sophie Scott, and I'm a cognitive neuroscientist. I study the human brain and human communication. And I've got a message for you from one of my favourite research participants, Doug Collins.
Hi, Sophie. Hi, everyone. I'm Doug, and I have the most contagious laugh in the world, as most people have said.
Laughter's a very basic kind of communication. It actually is sending a very important message. It's sending a message to people that you're happy, you like the people that you're with, you feel friendly towards them. And it's also, if you notice there, a very funny kind of sound. In fact, laughter is a lot more like an animal call than it is like the speech we normally do. And in fact, there's a reason for that. We are not the only animal that laughs, that sends messages with their laughter, in fact. Shall we have a go at making some animals laugh right now? Yeah. Thank you, yes, definitely. I'm delighted to introduce you, and you have to use tiny little non-frightening finger claps to introduce to you India Woods and her rat called Mould. Finger claps. Ooh. Hello. Hello, India. Hello, Mould. I'm so excited to meet you. You're fantastic. Now,
there we go.
Does Mould laugh ever?
He makes some noises.
Excellent. What do you do normally to make Mould make a noise?
You tickle him.
Oh, okay. And where's the best place to tickle a rat?
Where you tickle a person. On his armpits, on his back.
There we go. Now, I don't know about you. I don't normally feel at my most ticklish when I'm being watched by about 250 complete strange people and I've been placed on a little podium. So I think what we might be doing is we might be making it slightly hard for Mould here to feel like having a laugh. So I think we've got some examples of his laughter from earlier today.
Yeah, this morning.
Can we hear that? So you can hear these little chirpy chirps. Now that actually is the sound that he's making when he laughs. And we know that it's something to do with laughter because rats, just like us, they laugh when they're tickled, they laugh when they're playing, they laugh when they want you to play with them. So it's actually a very important communication sound for rats and for humans. Thank you very much.
Thank you.
Bye-bye, sweetie. We share a common ancestor with rats going back 65 million years. So it's possible that laughter really is a very old communication sound for mammals. It's possibly, certainly one of our earliest communication sounds. But what would the very first communication sounds have been on Earth? What would have been the first animals to communicate with sound? Who would they be? Well, to think about that, we're going to look at these charming specimens. These are insects. They're actually crickets. 500 million years ago, insects crawled onto the Earth, and they're therefore very good candidates for being the first animals to use sound for communication in the air. So, if we look closely at these guys, we can see that they've got legs and they've got wings. I can hear that they're not making a sound, so we're just going to play in an example of what it would sound like. You hear the chirping sound? It's actually a very, very basic communication. What they're saying is, I am here. I am a cricket, and I am here. It's basically a mating call. The most basic sound you could have, really. I'm right here. Whenever you're ready, I'm here. So, and they're making it in this fantastic way. It's just simply the best word in science. They make it via a process called stridulation. They are stridulating. And what stridulation means is they're rubbing body parts together. And the way the crickets are doing this is they're actually rubbing their wings together. If we look at a close-up image of the base of a cricket's wing, you can see it's got this very regular notched surface. And when they rub their wings together, you get a very regular sound coming out of that movement. There's actually a musical instrument that humans use that makes a sound in a very similar way, and I'd like a volunteer to have a go at playing this for me. Can I have you with the glasses and the scarf? Thank you very much. Thank you very much. Now, what's your name?
Alex.
Alex, it's lovely to meet you. May I present you with a guero? Okay. How do you think you might get a sound out of that? It's a bit like the crickets. Excellent. Go a bit more slowly. Fantastic. Top guero playing. Now you can see there that actually the regular notches are giving you regularity in the sound. The crickets aren't just making a noise, they're making a noise that's got some recognisability to it. It's got some information in it, and it's kind of built into the structure of the way that it's making the sound at all. Thank you very, very much. I'll have my guero back. Thank you, Alex. So Alex was basically stridulating for you there. She was rubbing two things together to make a sound. But actually, generally, whenever you hear a sound, it means something happened. There was some kind of action in the world. If there aren't any movements, if there aren't any actions, there are no sounds. And we can see there how the regularity in the shape of the guero or the cricket's wing is giving you regularity to the sound. And that's important for the crickets. But how do we hear that as a sound? How do we experience that vibration as something that we can actually perceive? Well, to think about that, what we need to do is look at a slightly more simple system. We're going to look at a tuning fork. Now, this isn't any old tuning fork. This belonged to John Tyndall, who was a scientist here at the Royal Institution. This is actually 150 years old. And John Tyndall did some amazing work. He discovered why we see the sky as looking blue and how the greenhouse effect can lead to global warming. What I'm going to do is hit one of his 150-year-old tuning forks, and hopefully we should be able to hear a sound. Now, the sound is being made by movements of that tuning fork, but I can't really see those movements as they're moving too quickly. So what I'm going to do is turn to a high-speed camera, and we're going to see if we can slow that down and look at it in more detail. To do this, we're going to need more light, because the high-speed camera needs more light information to get good images. Thank you. Okay, I'm going to hit it again. You can see there I'm hitting it, and immediately the tines of the fork start to vibrate. And that's what's causing the sound to happen. That's giving us something we can hear. And it's doing that by causing all the air molecules in the atmosphere around us to start to vibrate. And what this sets up is a chain of movement of these air molecules vibrating back and forth. You get these waves of air molecules stretching out and being compressed. And when it reaches our ears, that's what we hear as a sound. It's very hard to imagine that with the air molecules. It's somewhat easier to imagine with a spring. So the air, like this spring, is extremely elastic. What I'm going to do is just put a single vibration into this spring. And you can see how it's being passed along. Although any one single coil of the spring is not moving very far at all. We get that pattern of waves of compression and stretching out. Thank you very much. Thank you. It's easy to see those vibrations in the spring. We don't really notice it happening in the air around us. But there is an extremely sensitive photographic technique called Schlieren photography that lets us record the disturbances in the air as the sound waves are passing through. So this is somebody about to clap their hands. And as their hands make contact, look for the sound waves radiating out. Did you see that pattern of movement radiating out from the hands? It's been slowed right down, but you can see that was coming from the source of the sound. Now, all sounds are made by movements, but how do our bodies pick them up and hear them? How do we decode sounds? Now, tell me, what organ do you use to hear sounds? Point to it. Yes, your ears, absolutely. In fact, the bits on the outside that we all just pointed to, that's just the outside of your ear. That's called the pinna, and what that does is it's a funnel for pointing all these air vibrations down towards the real ear, which is actually located down, tucked away inside your head. And what this is doing is it's trying to turn the vibrations that are sending sound over to you into something that the brain can perceive. And what the brain wants is the information in an electrical form. Your brain deals with electrical signals. So how do we turn these vibrations of the air molecules into an electrical signal? Well, this is a demonstration of that at work. So we have air molecules moving down, and it's funneled in by your pinna towards the eardrum. And what you have at the eardrum is just like a drum. It is vibrating when the air molecules push against it, and then it transmits that pattern of vibration through 3 tiny little bones, the smallest bones in your body, and then that is sending a vibration into one end of what's called the cochlea. And the cochlea is a fluid-filled tube, and that fluid starts to move with the vibration, so it's all still physical movement. And in the cochlea, there are these tiny little cells called hair cells, and they start to bob up and down, and they have small filaments called the hairs. When those move, when the whole thing bobs up and down like that, and that is what sends an electrical signal to your brain. So the entire ear is a machine for turning the vibrations of the air into something your brain can hear as sound. And of course, if anything goes wrong with this entire chain of events, you will have a problem with your hearing. The ear has moving parts, those moving parts can break. So communication with sound is about creating movement of molecules which another creature can pick up, detect, and experience as sound. However, we're living in quite a noisy world. We only tend to notice sounds that we can hear, but there are lots and lots of communication sounds we can't hear. So we've got an example here of another tuning fork. Now this tuning fork is much larger than the one I showed you before, and this one will vibrate at a pitch much too low for us to hear. So how do I convince you that something's making a sound that you can't hear? Well, I suppose I could just ask you to believe me. But let's try and do it with a demonstration. What we're going to do here is we're going to put sound into the tuning fork through this loudspeaker. You'll hear the sound at first because it will still be in a range where we can hear sounds, and then it will drop down such that we can't really hear it at all, but we will start to see the tuning fork itself begin to move. Okay, you can put your hands over your ears for this. Right. Still hear that? Still hear that? Going down. Now if you look, you can see the loudspeaker moving. There is sound coming out of that, and it's starting to vibrate the tuning fork. So there's energy coming out of here we can't hear. That's called infrasound, sound that's simply too low for us to be able to detect. And infrasounds can be exploited by animals, normally animals much larger than us. Animals, in fact, that I'm very fond of, elephants. Now, I'm very sorry to say, I haven't got an elephant to show you. We can't get them in the lift. So I went to ZSL, Whipsnade Zoo, to meet qualified elephant keeper Ben Abbott and find out more. So the very low-pitched, low-frequency sounds the elephants make, it gets called infrasound.
Yeah.
Are there particular situations in which they use that? Does it work better in some environments than others?
Yeah, I mean, generally speaking, the infrasound that an elephant will use, because they can communicate over such vast distances. So When a herd of elephants is travelling, they spread out, which could be over, say, 50 to 250 metres apart.
Right.
And if you can imagine, one's all the way over there and one's here, and
Yeah.
you know, one wants to say we're going this way, just for an example, they will communicate through low frequency.
And so, is there evidence that they're picking up all of this sound just with their ears, or is there any other way that they're detecting that infrasound?
Yeah, so technically there's two ways really that elephants tend to favour. I mean, obviously they have got very big ears, but the other way they pick up is through their feet. They've got a big squidgy cushion behind their toenails, so when they walk it sort of sucks up, and when they put their foot on the floor it increases the surface area. Now if they're walking over vast distances, they can actually pick up these vibrations, so by putting the foot flat on the floor they feel the vibrations, whatever the communication may be, through infrasound.
So the elephants are really hearing the sound in two ways. They're experiencing it in two ways. They hear it as a sound, and they're also picking it up by feeling it in their feet. And the real advantage of that is that low frequency sounds pass very, very well through solid things like the ground. And that means that actually the low frequency sounds that they're making with their infrasound can travel a long way and be detected through another elephant's feet quite some distance away, in a way that a low frequency sound might struggle to be carried by the air. There's just one advantage of sound, and in fact, sound is an incredibly powerful way, efficient way of sharing communication information. It's very fast moving. The speed of sound is around 300 metres per second, so you can get a signal out there very quickly. It works in the dark. It works if something's behind you. It works if your eyes are closed. When you hear a sound, it means an event has happened. It can suddenly start. This is one of the reasons why throughout nature, when an animal wants to send an alarm signal, if it can do, it will do so with sound. But actually, we don't only use sound for very, very basic things like alarm calls. Because once you've got a sound, you can vary how loud it is, you can vary what its pitch is, you can vary its rhythm, and you can have interactions with sounds, you can have conversations with sounds. And I've got quite a surprising example of one of those conversations now. I'm going to play you a sound, see if you can recognise it. Anyone know what that is? Yep. It's not a vacuum cleaner. We're not quite having conversations with those yet. Any other guesses? Yes? Yep. It's a mosquito, yes. One of the horrible things that you hear flying around if you're somewhere warm enough to support mosquitoes. Unlike vacuum cleaners, mosquitoes make this sound, and we don't quite, I always assumed they were kind of saying, I'm in your hotel room and I'm going to bite you. But it turns out they're sending a rather more complex signal than that. And to tell us more about this, I'd like to introduce from the University of Greenwich, Professor Gay Gibson and Lionel Fougère. How are mosquitoes making that sound?
That sound is just purely the sound that's made when they beat their wings to fly.
Okay, so when they're flying, it's the sound they make.
Exactly, yeah.
And is that the whole story? Is that the only thing that's going on?
It's not the whole story, no. We've known for a long time that male mosquitoes can hear the sound of a female flying by. So we know it's got something to do with mating, but we didn't know the whole story until we investigated it a little bit further.
Okay, and is that the setup that we've got here?
Yeah, that's
Would you
what we've
like
got
to
here.
take us through it?
Yes, sure. So we all know that sound, that irritating sound that mosquitoes make, and we can study it more in depth by recording the sound that they make. And so we've done that here. We've brought in the apparatus that we used. That's a mosquito that's flying.
So what we can see here, there are two mosquitoes, and they're held just with a little bit of beeswax on the end of a...
Of a very fine, fine wire.
Okay.
And then on top of that, this yellow box there, that's an old-fashioned phonograph needle that we used to listen to records with. And they're still very useful. They pick up very, very fine vibrations from that wire to listen in on the mosquitoes' wing beats.
Okay. So at the moment, they're not flying because...
That's right. So when they've got a piece of paper under their feet there, they think they're on the ground, so they fold their wings back. But if someone could help us demonstrate this...
Yeah, we need a volunteer. Can I have you there with the check shirt and the dark jacket? Thank you very much. What's your name?
Sachin.
Sachin. Now, Sachin, I need to emphasise to you the importance of being really super gentle with the mosquitoes, okay?
You don't want to hurt them.
Thank you very much, Sachin. Now, Gay's going to tell you exactly what to do.
Okay, if you
Do you
come
want to
around
step forward?
here, I think you can see this little piece of white paper there. So in a minute, I'm going to ask you to take the paper away, and then we're going to listen to the sound that we hear. So this one is a female mosquito sound. Could you please gently take that little piece of paper away? Oops.
And she's immediately making a sound.
Hear that? That's the female's wing beat frequency.
Okay. Can we hear the male?
Yeah, let's do that. I'll put this one back myself. Would you like
Okay.
to take the male one away? Listen to this one. What's different?
It does sound very different, doesn't it?
Yeah, it's much higher tone. The
Okay.
males have the high voices and the females have the low voices. But the more interesting thing is what happens when they can both hear each other. So we're going to turn these mosquitoes off now.
Okay. So now we're going to take them both off. You okay?
Yeah.
Sam?
Okay, listen what happens when they can hear each other.
That's the female. There's the male. It sounds like they're bringing their voices together.
They are indeed. They're going up and down a little bit, and
Hang on. Is this a duet?
it is exactly a duet. And they can make this interaction between each other to help identify, are you the right species? Are you the one I want to mate with? So that's the way they communicate whether or not it's a good match.
It's a love song. I can't believe it. Sachin, thank you very much. Thank you. That was fantastic. And beautiful work. We can look at this on the screen. So, Gay, I think you've got a visual example of this. Is that right?
Yeah, we have a recording that we made earlier.
So this is a visual representation of that song, that duet that you recorded earlier. Can you
Yeah.
talk us through this?
Yeah, certainly. So here are the two mosquitoes. This is the female going along at a steady frequency. And here's the male. You can see he's going up and then down. And then we can
Can we hear that?
hear that, how that sounds. Dipping right down low.
Okay, and then they're coming towards the same pitch.
Yeah, they're having a little dialogue.
It really is in harmony, isn't it?
Till finally they settle on the harmony.
It's extraordinary. I don't know if I'm emotionally ready for really romantic mosquitoes. What they're doing is producing a song the whole time. The whole time they're flying, they're doing this harmonisation. Why can't they just look at each other? Why do they need to do this?
Well, they need to use sound because most mosquitoes are very nocturnal, so they don't have very good vision. But sound will carry much further than vision.
And they're not just emitting the sound at each other, they're actually changing their sound till they sound similar.
Yes, that's right, yes. They need to keep flying to be getting anywhere, but then they're also simultaneously, independently changing this frequency in order to come to a decision to mate with each other.
Amazing. Thank you very, very much, Gay. Thank you
Very
very much,
welcome.
Lionel. Animals aren't just using sounds to signal alarm, they're not just using it for mating calls. You can see here they're using the sound in a really complex, nuanced way for a real conversation. And for most mosquitoes, it's incredibly important that they can manage this. It's vital to their mating success. So we've seen stridulation being an excellent way of making sound. We've seen beating wings as another way of making sound. Now, another way that you often find sound being produced and controlled in the animal world is by using breath, controlling breath. Now, I've got some examples here of creatures who are very good at using their breath to make a sound. These guys are Madagascan hissing cockroaches, and what they do is they use breath to produce an alarm call, and I need a volunteer who was simultaneously extremely brave and also going to be very, very gentle with a Madagascan hissing cockroach. Come and pick one up for me. Let me have a look. Can I have you in the The red jumper, thank you very much. You feeling brave? Thank you very much. Now, what's your name? Orla. Lovely to meet you, Orla. Now, would you want to have a go picking one of these guys up for me? What we're going to do is see if we can see what sound they make when you do that, okay? So you and I need to be quiet. I'll put the mic in, and then you reach in and very gently pick one up. Amazing. Thank you very much, Orla. Thank you. So I'm going to suggest that we bring out a really qualified wrangler of cockroaches to go in a bit more detail. We're going to have a look at these guys and actually how they make these sounds. Is that okay? This is Ed. Okay. So if we look close up, so this is just the cockroach that Ed's holding up to the camera. We can see along here, those are spiracles. That's how insects get air into their body for respiration, how they're getting oxygen in and carbon dioxide out. It just diffuses into the holes. And what these cockroaches can do is they can close all but one of these spiracles and then press their abdomen in to force all of the air out through just one hole. And that's how we get this tss sound. Okay? Coming out from the side here, okay? Thank you very much, Ed. Now we, like cockroaches, move air around to breathe. But we do it slightly differently. We're not letting air permeate through our spiracles. We draw air in and out of our lungs, and that's how we breathe. And we, like lots of other mammals, have turned that into a way of making a sound. Now, we don't make a noisy hissing sound. We produce a rather more regular vibration sound, a bit more like the cricket's wings. Now, how do we make this vibration? Well, can you all just put your hands on your throats for me? And now go sss, like that hissing cockroach. I can't feel anything happening here. Now try that again, but now go zzz, like you're saying zoo. Zzz. What can you feel? You can exactly feel a vibration in your throat. Now that's actually the source of the sounds that we're using. It's in what's called the voice box, also called the larynx, and inside that there are two pieces of tissue called the vocal folds, and we vibrate those to make that sound. Now, let's see that larynx in action. I'd now like to welcome Professor Martin Birchall and willing soprano singer Francesca Ciegina. Fantastic. So we can ask you to sit down. And all of this is being operated by Idris. Martin, you're a consultant head and neck surgeon at UCLH.
Yep.
And you, Francesca, are a soprano singer from the Royal Opera House Jet Parker Young Artist Programme. And what we're going to do is use this rather alarmingly large piece of equipment to have a look at a larynx in action, I understand.
We are.
OK, so what actually is this?
So this is equipment that we use in the clinic, in the hospitals every day, and it's a nase endoscope stack, and we use it for looking at the throat and diagnosing people.
OK, and can we actually do that now?
Absolutely we can.
OK, you ready for this? Now, what's the actual device like?
Yeah, so what we've got here is there's three bits to this. We've got a light source here, we've got a processor, and we've got a strobe light generator. This itself is the endoscope. In the old days, these used to have, they were fibre optics, and so you'd get an image that was made up like the eye of an insect. Nowadays, we're fortunate enough to have very high definition cameras, much better than the ones in your phones, right on the end so we can see right inside.
OK, so can we do that now? Is that
Absolutely.
all right with you?
Yes.
OK, so we're going to drop the endoscope down, actually, to look right at Francesca's larynx.
That's precisely what we're going to do.
You'll be able to see the image on the screen here.
Okay, thank you very much. So just breathe gently through your nose. Relax your shoulders. This is going to tickle a little bit. Could I see the screen, Idris? Thank you very much.
So is that the back of the nose?
So no, we're actually going through the nose at the moment. The nose is very important for the voice, actually. It's an air conditioning device. So it warms, humidifies, filters the air that we breathe to make sure that everything that we breathe in is nice and clean. That's why it's bad to breathe through your mouth.
And that's the larynx.
It is. So what we're looking at there, it's a very alien-looking thing, isn't it? Is the larynx in the middle of the view there. The vocal cords are the two grey things moving in and out, forming a V shape in the centre. The big floppy thing is called the epiglottis. It's like a trapdoor that stops food and drink going down the wrong way. And the two round things towards the back are called arytenoids. They're bones that move the vocal cords in and out.
Francesca, would you feel okay to just sing a note for us?
Okay. Any note?
Absolutely.
Go for it.
So that I could hear, I could see that but the larynx came together. I couldn't see them moving.
You'll see it now. So we're now switched to a different light source that's going to flash light out of phase with the fundamental frequency of the sound that she makes. Basically, it's strobing like in discos when I was a young man a long time ago. It slows down movement, so you should see this here. So if you like to make a slightly higher frequency sound, Francesca. Very good.
Oh, well done.
And now could you do a glissando for us, from as low as you can to as high as you can?
Okay. Feels so weird. Okay.
Beautiful. So you can see the vocal cords lengthening and shortening.
Francesca able to move her vocal folds so very quickly. She's moving them around 2,000 times a second, much too fast for us to be able to see. Now, how fast can you move your body? Clap your hands for me. I want to see how quickly you can clap your hands together. Oh, that's good. Oh, we've got some good clapping there. Some top clapping there. Yeah. Okay. Now, I can't lie, I could still see all your hands moving. You weren't going as quickly as the vocal folds. Let's try it with your feet. How quickly can you tap your feet on the ground? Very good. That's very good, very quick. I can still see your knees moving. You're not going quite that fast. So, let's try something else. Blow a raspberry at me, please. Okay, enough raspberries. Thank you. Thank you. Now, that was fast. And that's because when you blow a raspberry, you do something very similar to how you make a sound at your larynx. Instead of moving your hands back and forth to clap or your feet up and down to tap, you don't move your lips up and down to blow a raspberry, you blow air through them. And that's exactly what happens when you are making a sound at your larynx. You blow air through. So you're not moving the larynx back and forth, you're using your breath to control that. And for this next demonstration of exactly how that makes us make a sound at our larynx, I need 2 big balloons. And a volunteer. Okay, can I have you, please? Thank you very much. Fantastic, thank you. Just ducking underneath this. Can you come and stand here for me, please? Okay. Thank you. Now, this is extremely normal, as I'm sure you'll agree. What's your name?
Isaac.
Isaac. Now, what I'm going to ask you to do, Isaac, in just a second, is to take a leaf blower and we're going to blow some air between these 2 big balloons. People in the audience, I want you to think, when we blow a big blast of air through these balloons, is that going to push the balloons further apart or is it going to pull the balloons together? Put your hands up if you think it's going to blow them apart. Excellent. Put your hands up if you think it's going to pull them together. Very good, slightly more for a part. In that case, what we're going to do is test this. So what I need you to do, Isaac, is pop on some safety glasses and pop these on, okay? And now, for your lifelong ambition, an enormous leaf blower. I'm just going to come this side. Now, I'm going to count you in and then you turn it on there and kind of point it right through the middle. Okay? 3, 2, 1, go. They're moving together, aren't they? They're moving together. Now keep going, keep going. And they're vibrating, and they're vibrating, and they're vibrating. Okay. Fantastic. Thank you. Now, don't go anywhere. So, if you thought that they were going to get pulled together, you were right. It's very counterintuitive, but what happens when you blast the air through the middle of these two balloons is something called the Bernoulli principle. And the Bernoulli principle says when you have air that's moving more quickly, the air pressure within that air is lower than in the surrounding areas. And what that does is it pulls the balloons together. It's not pushing them further apart, they're pulled in. This is just like your shower curtain sticking to your leg when you're in the shower because the air is being moved around by the movement of the water. The other thing that you'll notice as we carried on, well, as Isaac carried on blowing, was that the balloons also then moved apart and then came back together and they started to bounce. They're being pulled apart by things like gravity, and then their Bernoulli forces pulling them back in again. And that's exactly what happens at your larynx. You hold the larynx vocal folds together in the larynx, you blow air through them, and they're pushed apart and snapped back together under these forces of elasticity and the Bernoulli principle. So that's giving us those fast vibrations. Isaac, thank you. Thank you. But is this the full story of how we make sound? We're making noise at the larynx by blowing air through the vocal folds and causing them to vibrate. The vocal folds are amazing. They are an incredible piece of anatomy. They produce phenomenal ranges of sounds, and they're kind of rich with all sorts of different kinds of potential information. It's very, very important in terms of how we communicate with sound, but it's not the whole story. If we record the sound from the vocal folds and play it back, it sounds like this. Anybody recognise that? It's Jack and Jill. So it's a very over-familiar nursery rhyme, which you can recognise because the sound at the vocal folds, it's got the right rhythm, it's got the right pitch. That's where you put that information in. But it didn't sound like a voice. It didn't sound like somebody talking. So where does this other kind of information come in? Well, it turns out it's not enough to make vibrations. What you need to do is enhance, amplify, enrich those vibrations. And that comes down to another property of how sounds work. That's to do with resonance. If we can exploit resonance, we can make our communication with sound work much more efficiently. So what's resonance? Well, resonance is just a characteristic of objects, things in the world. From molecules up to mountains, things, objects, have a frequency at which they will maximally vibrate. And we can use this property when we're making communication sounds to help maximise the sound vibrations that we're producing and therefore enhance their communicative properties. I've got to show you how this works with an extremely simple demo. So you can think of everything as having a rate at which it moves most efficiently, at which it will vibrate maximally. And here we're seeing how that can be affected by the shapes of objects. And here we've just got, as our objects, we've got 4 lovely Christmas baubles. And for the purpose of this demonstration, I want you to think of a whole thing, the bauble and the string, as being the shape of the object. And what I'm going to do is move this ball here. And what I want you to do is watch what happens to these guys. Now you should notice that one of these Christmas baubles starts to move at a more exaggerated rate than the other ones. Can anyone call out the colour, the one that's moving most? Red, exactly. Now what does red have in common with this one? It's the same length. So the shape, the overall shape of the whole thing is most similar across those two. And it's meaning when I move this one, it's putting in the right kind of movement to vibrate something of a similar shape. So if I change the shape of this guy by shortening the string and then do exactly the same thing, I'm just going to set this one moving. So now you can see with this different shape, a different Christmas bauble is moving maximally. And what's happening here is I'm putting the right kind of force in at the right kind of speed to cause maximal vibration for this Christmas bauble. And of course, we do this all the time. We have a very intuitive understanding of how we can put the right kind of force into things that we want to move. If you ride on a swing, you know how to push that at the right kind of speed and the right kind of force to make yourself swing. And you do the same thing when you use your voice. When you make a sound with your voice, you're actually exploiting that kind of pressure of your air to get the right kind of resonance properties for the vibrations that you make. Sounds are made by vibrations, and those vibrations are made bigger when the objects that we make vibrate can hit their resonance frequency. And this, amongst other things, can mean the sounds can be louder. Now we can see a more dramatic demonstration of this if we take a more complex object and explore its resonance characteristics. What we're going to try and do is find and exploit the resonance frequency of a wine glass. Now, when you make a wine glass make a sound like this, what you're doing is you're finding the resonance frequency. So I'm putting in the right kind of force at the right kind of speed to start resonating this glass, and we can hear that. However, if we record that sound and then we play that sound back into the glass, we can see much more dramatic effects of that vibration. And at this stage, I just need to ask everybody to put their earplugs in, and you guys put your earplugs in and your safety glasses. So what Fran has done earlier is she's calculated the resonance frequency of this wine glass, and she's going to generate the right sound and put it through under great levels of intensity out of this loudspeaker. And we'll start to see what that does to the wine glass. And we can see this because we've got the high-speed camera again, so we need more light for that, and you'll see that appearing on the screen. Okay, so everyone got their ears covered up? Off we go. There we go. That's amazing. So if I leap over the debris, can you see how much that wine glass is moving before it breaks? How much those vibrations are causing it to distort and shake? And just when you think it can't possibly tolerate that much movement, it stops tolerating that much movement, and we see the whole thing break to pieces. Whoa. That's the power of resonance. If you want to send your message further, resonance can really help you. But how are we exploiting resonance in our own bodies? I mean, to be brutally honest, we're not exploding wine glasses or anything dramatic like that. Actually, we're doing something a bit more like a musical instrument. I've got an example of a musical instrument here. Thank you very much, Natasha. So we've got the basics of a musical instrument. We've got a string. I'm going to make that string vibrate by plucking it. Now you can kind of hear something, can't you? And you can see something's moving. There's not very much sound there. What we can do is make that much more impressive by bringing in a bit more resonance. Thank you. So this is just a tea chest. It's an empty tea chest. Well, it's not empty. It's filled with air. And what we're going to do is use the resonance properties of the tea chest and the air inside it to really exploit the vibrations that we're making with the exact same string, the exact same stick that you just saw before. We do that, you can hear a sound, a much louder sound. Where's that sound actually coming from? We're hearing the sound of the string? We're probably not. We can actually image that with this fantastic device here. This is actually an acoustic camera, and it's a really rather beautiful array of microphones. It looks like a sort of spectacular tree. And what that's going to be used for is to give a spatial location to where sounds are coming from. So if I make a sound, you can see that the sound source is coming from the front of my face, which is correct. That's how I was making that sound. So now if we try this with our bass and see if we can see that making the sound, it's the air. It's the vibrating air that's causing the sound. It's coming out from the bottom of the bass. There we go. Thank you very much for looking at the camera. So that's a simple demonstration of how adding in the resonance here of some air inside that box helps us hear the vibration of that string completely differently. And we're doing something very similar. We're taking the resonance characteristics of our own vocal tract and we're using that to shape and enrich the sound we make at our larynx. So if we look here at my cutaway head, this is just showing you the shape of the air tubes that we're sending sound into when we make a sound at our larynx. So the larynx is sitting down here. It's sitting down actually in the windpipe. It's quite low down in humans, much lower down than it is in other primates. And what that gives us is a much longer tube for making the sounds that we make with our voices. It's a long way from our larynx to our lips. And that's called our vocal tract. It's actually made of two tubes. We've got one tube coming up through our mouth, one coming up through our nose. And there are two aspects to this. Our lowered larynx gives us a longer tube to make the sounds with. It's giving us this richer sound. And also, what we can do is we can modify the shape of our mouths and change the resonance characteristics. So if you all go E, oo, now that's you changing the resonance characteristics of your own vocal tract, and that's giving you a different sound. So we have a richer sound, we have a more complex sound. It's as if we had a musical instrument where we could change the shape of it all the time, and we use that really importantly for how we communicate with sound. Our lowered larynxes are giving us this richer range of sound, and in adult men, we see another movement down of the larynx. In adolescence, boys' voices break, and what that literally means is the larynx moves physically further down, and you can see an Adam's apple in the neck of most men. This gives men an even longer tube to make the sounds of speech and their voice with, and it gives them a deeper, richer sounding voice. But it turns out humans are not the only animals that have a larynx which we can maneuver in this way. Fallow deer, male fallow deer, compete to mate with females. Professor David Reeby from the University of Sussex went to look at how the bucks use their voices to communicate their size and try and impress those females and each other.
Hello Sophie, hi everyone. So today we're in Petworth Park, and this time of the year the fallow deer engage in what we call the rut. During the rut, the males produce a very large number of vocalizations called groans. And these groans are very low pitch, and we believe that they produce this vocalization in order to communicate information about their body size. We're going to play back groans, which have been resynthesized, where I've either lowered the resonances so that the buck sounds a lot larger than it actually is, or where I've raised the resonances to make it sound a lot smaller. So what I'm going to do now is to play the small version. Clearly puzzled by the playback. Now I'm going to play back a very large buck. Look at this guy. So we definitely got their attention here. And you can see he's clearly intimidated. So I think you could really see the response of the buck to the first sequence where the caller sounds smaller. We had a quite timid reaction from the target animal, whereas when we played the grounds where the resonance had been lowered to make the animal sound a lot larger, we got a much stronger response from the target buck.
David was actually the first scientist to realise that deer were able to do this with their voices. And he's been taking CAT scans of deer vocal tracts. You can see that here. So that's the length of the neck. And it's giving you some idea of how far they can move their larynx up and down. We think we've got fairly impressive vocal tracts. Deer are much, much larger, and they're moving their larynx really a long way up and down them to create this incredible range of sounds. The deeper voice, maybe it suggests power and strength. Maybe this has some similar role in humans. Maybe this secondary descent of the larynx that boys go through in adolescence is adding in aspects of their voice which are potentially conveying dominance or size. It's certainly possibly giving men the sound of a bigger body without actually having to grow a larger and more expensive bigger body. We're seeing sounds generally, however, as being something we can think of as actions. All sounds happen because something happened in the world, and the things that interacted to cause those sounds to happen also affect the sound. As the bodies get bigger, the sounds get deeper and they get richer. We've seen a variety of different ways that animals can communicate and are orchestrating this physics of vibration and resonance to help communicate with each other, to send and receive messages. And of course, the more you can vary these sound waves, the more complex the messages you can communicate. Now, humans are exceptionally good at really rapidly and precisely modifying the sounds we make when we use our voices. We can shape and interrupt the flow of air with our tongues, our lips, our teeth, our jaw. And of course, this is one of the main ingredients for one of our most important sound communications, speech. And to show exactly how we do this, please welcome my friend and colleague, Reeps. Hi. Thank you. Now, Reeps, can you start by just taking us through some plosive sounds? Plosive sounds are sounds where we make a closure with our lips and then sort of spit the sound out.
Yes, of course. But, t.
I've worked in speech for many years, and I always used to start all my talks by saying human speech is the most complex sound in nature. And then I met Reeps, and I realised, because you'll have just spotted, he was beatboxing. He's one of the world's greatest beatboxers, and he does these incredible, amazing noises, the speed with which he's doing things, the sounds he's producing. It's so much more than we do when we're talking. And we can actually look at that in a bit more detail. Are you OK to come and stand over here?
Yes, of course.
OK. So what we've done is we've put Reeps into our MRI machine, and we've run that like a video camera so we can actually image his vocal tract and how he's changing it while he beatboxes. And you can see that on the monitor here.
Oh, yeah.
Thank you. Thank you. That's absolutely extraordinary. You could hear at certain points there Harry was producing at least 2 different sounds at once. And that's not technically supposed to be possible. Apparently, no one told you. Now, is it the case that this is just a learnable skill? Did you teach yourself this?
I started because I played lots of instruments when I was younger. I wanted to make music all the time, and it's a way to internalize music for you very quickly. And I completely taught myself. Listening to music, listening to things that are out there, it's possible for people to create their own music with themselves all the time.
And could any of us learn to do this?
Absolutely. Every single person in this room can start exploring sounds. We all use 26 sounds in the alphabet. 3 of those sounds can easily become music, and you're all welcome to explore.
Excellent. Thank you very much, Reeps.
My pleasure.
You wouldn't mind just sitting there. Thank you. Thanks. Don't go anywhere. So one thing that's really striking is that human vocal abilities, if anything, are over-engineered for speech. I thought speech was so complex, and then I saw things like beatboxing, and I realised we're actually doing almost the bare minimum when we talk to each other. So I wonder if there might be some other aspect of our communication and our voices that might have driven our evolution of this really extraordinary musical instrument that we have. So please can I introduce my last guest, Catherine Woodward. Now, I've made a movie of you in our scanner, looking at your vocal tract. Can I position you here? And can you sing along to that for us? Is that okay? Thank you very much. You can see in Catherine's voice the range and the shape she's creating in her vocal tract to produce this sound of such power, such strength, such thrillingness. And of course, we can all potentially learn to do this. We might never be as good as Catherine, but it's a learnable skill. We all learn to speak. We can all learn these other kinds of vocal abilities. And one theory does suggest that what we might be looking at, because we can do so much more than we do when we're normally talking to each other, we might have evolved this ability for vocal gymnastics before we were ever using it for speaking. Possibly, our vocal range and complexity may have been a way for our ancestors to win mates or defend territories, much as the same way we see birds nowadays using sound to impress other birds. Once we'd evolved this absolutely extraordinary musical instrument of the human voice, maybe speech was almost an invention, an afterthought. It's an afterthought, of course, that has created the world we live in through the gift of language. Whether you are a cricket or a cockroach, a deer or an elephant, the ability to communicate with sounds can be absolutely critical to your survival. Thinking about the human voice as an instrument for social, emotional, as well as spoken communication can help us understand possibly why we ever evolved such an extraordinary musical instrument of such complexity and range. So for our finale, I would like to invite you and our guests, both animal and human, to really try and show the full extent of what our voices can do. Harry, Catherine, if I could have you back, and let me introduce Stephen, who is our composer for this evening. Thank you. 3, 2, 1.